Hello, everyone. This is Mohsen Mescar. I'm a postdoc at the UKP lab at TU Darmstadt. And I'm going to give the third lecture of the Deep Learning for NLP course. The title of this lecture is Training as Optimization and Neural Language Models. In this lecture, we talk about three main topics: training as optimization, backpropagation, and language modeling. In training as optimization, we try to model the a learning algorithm as an optimization problem. And we show that by solving an optimization problem, you can learn to solve a task. Then we introduce the backpropagation algorithm, which is an algorithm that helps to train a neural network. And at the end, we discuss about language modeling task, which is a fundamental problem in NLP area. As I recall, we know that when we have a supervised learning algorithm, the input to the algorithm is a training set where X's are input examples and Y's are corresponding labels to those input examples. So if X would be movie reviews, Y can be the sentiment of these reviews. For example, they can show if a review is positive or if a review is negative. X can be also an email, and Y can show if the email or the text of the email is spam or is not a spam. As another example, X can be a document and Y could be the topic of the document. It could be a sport or it could be news. Or in another setup, X can be a text in German and Y can be a text in English. So a new supervised algorithm receives as input a pair of X and Y, indicating the input examples, and Y indicating the true labels or true outputs that we expect our model returns when it sees input X. The goal of a learning algorithm is to return a function f. So the output of the learning algorithm is going to be a function f that accurately maps input examples to their desired labels. So if we look at a learning algorithm like a box, then the input to this learning algorithm is X and Y, or the data that we have, and the learning algorithm learns a function that accurately maps X's to Y's. And then it returns this function f. But somehow we need to know if f works perfectly, right? So somehow we need to measure how well f is working. Here we can define the loss function. So let's say the function L that is defined over true labels y, and the labels predicted by, or the outputs predicted by our network y hat, quantifies the loss suffered when predicting y hat why the true label is y. In other words, the loss function measures how far the prediction of the network is from the true outputs. So given a labeled training set X and Y, a per instance loss function L, and a parameterized function Fx and theta, we define the corpus-wide loss with respect to the parameters as the average loss over all training examples. So let me use my pen here. So let's say we have function f, right? So we train function f, which is a parameterized function, and it has parameters theta. We use training sample xi as the input to f, and f returns an output y hat. So since this is a prediction, we use the notation y hat. And the goal is that y hat be similar as much as possible to yi, or the true label associated with input xi. So we used function L to compare the predicted output with the true label, with the true output yi, and to measure how different this prediction is from the true output, right? And since the data set consists of n examples, we compute the average over all of these examples. So the corpus-wide loss is defined as the average of per instance loss. So, good. But as you notice here, the corpus-wide loss is a function of theta, is the function of parameters. But why is it so? The loss, look at the formula of the loss here. Loss relies on y hats, right? So let me clean this. And we can use it again. So loss here is defined over y hat. Yi is fixed because it's given in the training set, right? We know an email is a spam or not. So this is fixed. So this is a constant value. So, but y hat is a variable and is the output of the function, which is defined over xi and theta, right? Xi is also fixed because xi is the input sample from the training set. This one is also fixed, but the only thing that can be changed is theta here, right? So we have one training set and we want to know what is the best function that fits to this training set. So if we have theta 1 and it gives loss 1, and we have theta 2 and it gives loss 2, and if loss 2 is less than loss 1, we say theta 2 is better than theta 1 because theta 2 yields a function that that more accurately maps input samples to the true labels. Okay. Okay, so as I said, in this view, the training examples are fixed and the values of the parameters determine the loss. Okay, now that we observe that, our goal is to minimize or optimize the difference between the predicted output and the true labels given in the data set. So the goal of the training algorithm is to set the values of the parameters such that the value of the loss is minimized. So our goal is to find the best value of theta that yields the minimum value of the loss. But okay, so this is so if we minimize this function, then we have everything. Okay, but what type of loss function can we use here? Let's look at some common loss functions that we have in NLP. The first category is Hinge binary loss function. As the name shows, this loss function is mainly used for binary classification problems. You want to classify a text as positive or negative. You want to say it is about sport, or it is about politics, or it is about science, right? So it is about a binary classification. So the classifier output is a single scalar y tilde, and the true output y is in -1 or +1. So let's say we map classes to some numbers like +1 and -1. If, for example, if y is topic, if y shows that the topic is news, we set it +1. And if y shows that the topic is about science, we set the label to -1, right? So in this way, we can move to some numerical space. And the inference rule then is very easy. The inference rule says that if the score our network predicts is positive, then the label is +1. And if the score is negative, then the label is -1. So let's say we have a network and we give it a text and it returns one number. So we look at the number. If the number is positive, we say it is +1. And if the number is negative, we say the class is -1. Okay, but how can we define the loss for each instance in the training set? We define the loss as the maximum between 0 and 1 minus the product of y or the true output or the true label and y tilde or the score that our network returns. So let's say the true label is +1, right? If the true label is +1 and the predicted score is also a positive number, then we have a positive number here, right? So 1 minus a positive number can be either between 0 and 1 or less than 0, right? And if the number is less than 0, the loss is 0, right? So we do not need to update anything. But if the number is between 0 and 1, then the maximum number is this number. So let's say 0.5, for example, then the loss value is 0.5. Then we get back and we update the parameter of the model. So, but why did it happen? The prediction was correct. The score is a positive number, so the label is positive. But why do we still update, or why do we still define some loss? Because of the margin that we have. We are using margin 1 to make sure that our model predicts the correct label with confidentially, with some confidence. We want our model to be confident about the prediction that it makes. So that's why we defined a margin here of 1. Okay, Hinge can also be extended to multi-classes. So instead of having, let's say, 2 topics, news and politics, we can have 3 topics: news, politics, and sports, right? And let's say we have the defined n topics or n class labels. And the output of the network then would be a probability distributions over these labels. So, so the number, so let me mark this here. So let's say the first number that we, so our model returns a vector, right, as the output. And the first number in the vector indicates how likely is that we have label 1 as the correct label. And second number shows that how likely is that we have the second label as the correct label. And yn indicates the probability of having label n as the output. So, and if we assume that y, or the true label, is also a one-hot vector, so meaning that one of these numbers would be, one of these labels is correct, and 1, and the rest is 0, then the inference is easy. So let's say intuitively you know that this number has the highest value among these numbers in the vector. So we say that the label of the input text or input is this one. Why? Because it has the highest probability. So we go through this vector and we look at the index of the item that has the maximum value. We use this index as the class label. So the inference rule is very easy. So we define it as selecting the class with the highest score. So prediction would be the argmax of the output vector, right? And now how should we define the loss? So let me use my pen again. So let's say this is the class that has the highest probability score, and the true class is this one. So we expect that this one, or the green one, has the highest probability, but in reality, what our network returns gives the highest probability to the second class. So how should we compute the loss? It's easy. So we compute the loss by defining the difference between these two scores. We say our model predicts y hat k, and the true label is, so if I want to show it, so we said that this one is the true label, this one is what our model returns, and we compute the difference between this and this. So we expect the difference between what the true label is, the probability that our model returns for the true label, minus the probability or minus the probability that has the, or that is the maximum among the rest of the items in the output vector. So if we try to increase the difference between these two, so we are pushing our model to give higher score or higher probability to the true class instead of other classes. Oops. Okay, so let me clear all drawings and then we continue. Okay. The other common loss function is log loss, which can be seen as a soft version of the Hinge loss with an infinite margin. So the input to the log loss is the output score of the network, the output vector of the network, and true labels. And what we do, instead of defining a margin one, what we do, we just plan to minimize the to maximize the difference between these two, to maximize the difference between these two. Okay. Now we can go to the binary cross entropy loss function, which is very important. It is used for binary classification with conditional probability outputs. Let's say we assume, let's say we have a binary classification task where we can map the true labels to numbers 0 and 1. So let me give you an example. We need to distinguish between two types of binary classification tasks. The first category is like distinguishing between two topics, saying that the topic of the text is about news or the topic of the text is about politics. But the other types of binary classification is yes or no classification. We want to say if an email is a spam or it's not. So it's like 0 or 1. If it is true or it is false. We want to say if a text is about news or it's not. So this is like a tiny difference that we can see between binary classification tasks. So let's say we have one email and we want to know if the email is spam or the class label is 1 or the email is not spam or the class label is 0. So the model output is the model output is only one score, and we map this score to a probability value, so between a number between 0 and 1, using the sigmoid function, which is this, right? And then we say that the output of the sigmoid function shows the probability of being class 1. So the output then shows the output of the sigmoid function, then shows if how likely is that the input image is a span, right? So it's class 1. And it's very easy then to define an inference rule. If the probability is greater than 4.5, we say this is a positive case, so it is a span. And if the probability is less than 0.5, we say this is a zero label, so it's not the span. Yeah. So the loss can be defined like this. So as you notice here, we refer to this loss also as negative log likelihood. And I will tell you why it's called negative log likelihood. Let's assume that the true label is 1. Then what happens? Okay, when the true label is 1, 1 minus 1 is 0, right? So the second term is 0, and we only have the first term, right? So here is a negative value, and y is 1, right? Because we assume that the true label is 1. So y is 1, and we only have the log probability, the log of the output of the network or the output of the sigmoid function. So, and we assume that the output of the sigmoid function is exactly the probability of this label, right? So, so we assume that this is the probability. So since this is the likelihood or the probability, then we have the log of the likelihood. So we have log likelihood, and we have a negative here. So we have a negative log likelihood. So if our model for a true label 1 predicts a probability of 0.6 or something, 0.7, or any probability greater than 0.5. So we try to push it further. So we try to push this probability to get close to 1. So we expect that our model predicts 0.8, 0.9 instead of 0.6. So we try to maximize this log, or since our goal is to minimize the loss, so we put this negative likelihood. So minimizing something that we want to maximize. So it's like we want to maximize this function or minimize the negative of this function. Right? And this story is also true for when the true label is 0. Then the first item is 0, and the same story happens for the second term here. Okay. Okay. Now that we also defined the loss function, we can get back to our training and optimization. We said that the goal of the training algorithm is to set the values of the parameters such that the value of the is minimized. So our goal is to find the parameter theta, or the best value for parameters theta, such that by using these parameters, loss get to its minimum value. But there is a risk with such an optimization. And the risk is that if the model works perfectly fine and we learn to predict the label of all instances in the training set, then the model overfits to the training set, and the model cannot generalize to some unseen examples. So to encounter with this problem, we define a regularization term, R theta. R theta, or this regularization term, takes as input the parameters of the model and returns a scalar that reflects the complexity of parameters. Of course, we not only want to learn the property of the training set, but we also want to keep the complexity of our model as low as possible. So we have defined the training as an optimization problem like this, but instead of optimizing for the loss, or instead of only minimizing the loss, We can minimize loss plus some regularization term. The gamma value here, the lambda value here is a hyperparameter to find a trade-off between how much a regularization term should be effective in this optimization problem. So if the lambda is very close to 0, so we would like our model to fit more to the training set that we have. And if lambda is close to 1, we want to push our model to generalize better to unseen examples. Let's look at some regularization terms that we have. Okay, before going that, so intuitively, we would like to drive the learner toward natural solutions in which it is okay to misclassify a few examples if they don't fit well with the rest. So yeah, so just like some intuition about the regularization term is that if some outliers, if our model or function f does not fit to some example, that's okay, but still we are ready to pay the cost of this, but instead we can classify some unseen examples, which is the main goal of any learning method. Regularization term considers the parameter values and scores their complexity. That's why as input they receive data. And in practice, the regularizers equate complexity with large weights and work to keep the parameter values low. So we don't want to have large value of the parameters, so we try to keep them as low as possible. Let's look at some common regularization functions. The first function or regularization technique is L2. It keeps the sum of the squares of the parameter values low. So let's say if our parameters are W or the matrix W, so we compute the square of all elements of the matrix or vector, and then we compute the sum of the square. We use it as the loss. In this way, the learner will prefer to decrease the value of one parameter with high weight by 1 than to decrease the value of 10 parameters that already have a relatively low weights by 0.1 each. So meaning that if you have one parameter with weight, one parameter with value 1, you prefer to decrease this value a lot instead of having decreasing value of 10 parameters that already have low weights. L1 regularization technique, it keeps the sum of the absolute values of parameters low. So instead of having this square here, we have the absolute value. The learner will prefer to decrease all the non-zero parameter values towards 0. So instead of looking all parameters in the same at the same time, what we do is that we look at each parameter one by one and try to keep all the values close to 0. Okay, and then we have elasticness, which combines L1 and L2 regularization in normal way, and then we have the dropout, which works differently from L1 and L2. That's why we do not discuss it here, but it will be discussed later in the course. Okay, let's get back to our training as optimization. We learned that the goal of training is to minimize a loss function and maybe a regularization term. So we want to minimize the loss over the whole training set plus some regularization term. And the output of this minimization should be some parameters that define our function f. Okay, so in other words, training equals to solving an optimization problem in math. Now the question is, how should we solve this optimization problem? The answer is a numerical method for optimization, which is called gradient-based. Gradient-based is not used only for neural network. It's used for any types of optimization problem. The only difference is that we can solve a optimization problem either by computing the optimal value directly, so on paper. So you take the derivations and just you make the derivation equals to 0, and then you find what the root of this function. Or the other way is the numerical approach that we explain it right now. So the intuition behind gradient-based optimization is something like this. Let's assume that we have a figure like this, and the x-axis shows the value of weights or parameters that we have, and the y-axis shows the value of the loss for each given weight. Right? And our goal is to find this place, right? So our goal is to find this value of weights as the best value for our parameters, because this value of parameters yields to the minimum value of the loss. Okay, so what we do, we randomly start from one point in one. We randomly start from some initial values of parameters, so or initial value of weight. So in another word, we start, for example, we start this way. We go up and we say, okay, here is the value of the loss. So here is L1, and here is W1. So we start from this point, and we find the loss is here. Good. And now we want to know if we should go up, or if we should go in this direction, or if we should go in this direction. Should we increase the value of parameters, or should we decrease the value of parameters? How should we decide? Our goal is to get here, right? So we should come in this direction. But how should we know in which direction? What we do is that we calculate the gradient. Is the gradient positive or negative? The gradient is negative. So the gradient is negative. But we want to improve these values, right? So we want to compute W2, right? So W2 should be W1 plus some values. Okay. So gradient shows that how fast the function decreases, right? So we can calculate the gradient. So let's say gradient of L with respect to parameter W in general. This is this value. And we know what is the gradient at point W1 with respect to W1. And we take it this, and then we move down, right? So we sum value, let's say we sum the step size, we move forward. So we call it the step size. To know how far should we go. So we take this and we move one step here, and then we move, and then we say, okay. Okay, and then we say here is W2, right? and the value of loss would get close to here. Okay, so let's see. We started from this point, and we compute the gradient, and we move towards the negative value of the gradient. What does that mean? It means that if the gradient is negative, we want to improve, we want to increase the value of the parameters. And if the gradient is positive, we want to decrease the value of parameters. So here, negative, here the gradient is negative. So here, gradient is negative. So we want to increase the value of the parameter. But if we had started from this point, the gradient is positive. Sorry, the gradient is, if we have started from this point, then the gradient was positive, and then since it is positive, we want to go in the opposite direction. So we want to decrease the value of our parameters, right? So if W0 was here, we want our W1 be here. So is that clear? So if the gradient is positive, we want to decrease the value. So we want to say W1 is W0 minus some value. So we want to decrease that if the gradient is positive. But if the gradient is negative, we want to increase the value of our parameter. So this is the main concept behind the gradient-based optimization. So let's intuitively see how it works. We repeatedly compute an estimate of the loss over the training set, and then we compute the gradients of the parameters with respect to the loss estimate. And we move the parameter values in the opposite directions of the gradient. So more formally, we can introduce a stochastic gradient descent like this. But here we see the online version of the stochastic gradient descent. As any other algorithm in computer science, we have an input to the algorithm and one output. The input, okay, so let me use my pen again. Okay, so the input is a function that we want to use as a mapping function between input and output, or the model. This is the output of the learning algorithm, right? And this is a parameterized function. So, and let's say the name of the parameters would be theta. And we also have a training set of input samples and a set of true outputs. And also we have the loss function. What we do in several iterations, we run a loop, and at each iteration, we sample one training example, x, y, and yi. And then for this example, we compute the output of the model. So we give, or we feed xi to our classifier or to our model, and we look at the output and we say, okay, this is y hat. And we give this y hat and y to the loss function and to estimate how bad it is, right? And then we compute the gradient of the loss with respect to theta, and we call it g hat. And here is the stochastic gradient step. Here is, so let me change the color. I will look at it. Here is the stochastic gradient step, or SGD. SGD here. So in this step, what we do, we take the value of the parameters and we either reduce some constant from it, or we add some constant to it. But the constant is calculated based on the value of the gradient, so meaning that how fast should we move and how much we should move. And the other thing is this negative value. So we always go in the opposite direction. So if the gradient is negative, we want to increase. So negative times this negative value is positive. So we increase the value of the parameters. But if the gradient is positive, then we have positive value here. So we are decreasing some value or some constant from the parameter values. Okay. So the task of the stochastic gradient descent is very easy. So it says that if you know what the gradient of your function or your loss with respect to theta is, then you can update the value of your parameters such that you get close to the optimal value. But why is it called online SGD? It's called online because we treat training samples one by one. We start from the first training sample, we compute the loss and its gradient, and then we update the parameters. Then we go to the second training sample. We compute the loss and we update the parameters, and so on. Okay. But the point is that when you run it online, you move, you jump you jump up and down. Maybe because training samples could be different, right? So the gradient will change a lot. So at each time you jump, at each update, actually you jump up and up and down. So the answer, so one other alternative is to use mini batch stochastic gradient descent. So the mini batch stochastic gradient descent, instead of treating, so let me use my pen again. So instead of treating samples one by one, we treat them as a batch. So we select M training samples and we make them a batch. And then we use this batch to compute the loss. So what we do is that for any sample in the batch, we compute the loss, and then we compute the gradient with respect to theta for that example, and we add that to the gradient value that we have here. So at these steps, let me change the color. At this step, or step number 6, what we have at this step, what we have is the gradient with respect to all samples in the mini batch. In other words, we do not update the parameters of the model until we computed the gradient of all examples in the mini batch. But in order to not be biased toward the number of samples that we have in the mini batch, we compute the average. So if we have 5, so we divide all gradients by 5. If we have 10, we divide by 10 to alleviate the impact of the batch size. And this step, or step number 7, is exactly the gradient step, exactly the stochastic gradient step, that we update the parameters based on the stochastic gradient rule. Okay, now the question is, if we can do mini batch, can we use the whole training set? Yes, we can use the whole training set, but the point is that using the whole training set is is computationally very expensive, because sometimes training set may contain millions of examples, and you cannot fit all these million examples in your trainings into your memory. So mini batch is kind of a trade-off between full batch and online setup. And it also it has been shown that when we use mini batch SCD, the algorithm converges faster to a good solution. When we say converges faster, it means it finds it needs fewer number of fewer iterations to get to the minimal value. And what should be the mini batch size? The point is that there is no rule for that. It is a hyperparameter. The smaller mini batch size lead often to better solution or generalize better. But okay, good. The only problem, but SGD works fine. But as any other numerical solution, it does not guarantee that you get to the global minimum or to the global optimum. Let me explain that. So let's say we start from here, right? The starting point is here. You update your parameter. So let's say you jump here, and you find here. So this is minimum, but is it really the minimum of all values that we have? So let's say this x show our parameters w, and this one show our loss function, right? Is this value the minimum value of loss? No, the minimum value of loss is here. But why didn't we find this? Because we have started from this point. What if we have started from this point? So we could move here, and then move here, move here, move here, and then end up in this middle. Okay. And what if we have started from this point? We could move here, and then get to this step. So if we find or if we get to the global minimum, really depends on the initial values that we use for our parameters for the starting point of the algorithm. What is the algorithm, right? So SGD is very sensitive to the initial parameter values or starting points, and also the learning rate. So we talked about the initial parameter values. Let's talk about the impact of the learning rate. So what happens if we have a small learning rate? So you start from this point, but at each step you take very, very small stop. You take a very small step. So your step size is very small. So you are very conservative. So you don't take a long jump, a long step. You do not jump. So you move very, very. You prefer to not change the value of parameters a lot. So it takes a long time to get close to the minimum value. But what happens if we have a very large learning rate? So when we have a very large learning rate, so it's very likely that we easily pass the minimum. So we take very large steps, so we come here, and then we take another large step and then we come here. So we pass the minimum and we come here. So right. So and then we come here, and then we come back, we come here, and we come back. So we never get to the local minimum. So what is the best solution? The best solution is to have some sort of adaptive learning rate. So we start from this starting point, and then we take large steps at the beginning. And as after several iterations, we reduce our step size or we reduce our learning rate. So we try to change the value of parameters less and less as we process through the algorithm. Okay. So we can easily use some adaptive learning algorithms like ADA-GRAD, ADA-Delta, RMS-Prob, or ADAM. ADAM is probably the most popular method for adaptive stochastic gradient descent. These models usually train faster than SGT because at the beginning they take long steps, and then they reduce their step size. And they found the solution they found is often not as good as that by SGD. So the solution could be first train with Adam and then fine-tune with SGD. But how should we solve the problem with different initial value with random initial values? The answer is that we can easily use different initial parameter values in different rounds of experiments, and then we report the average of the scores. So in the first run, we use theta 1, and in the second run, we use theta 2 to initialize our parameters. And each run, we complete each run and all experiment in each run to compute the performance, right? And at the end, we report the average performance over these samples. Okay, if we have one simple function, a stochastic gradient descent, works perfectly fine. But the problem with neural networks is that the function is very complex. It's usually multi-layers. That's why it's called a deep model. And the output of the first layer is the input to the second layer. And the output of the second layer is the input to the third layer. So there is a nested structure over layers in a deep learning model. So here we want to discuss how we can calculate the gradient of a complex function like a neural model. And the algorithm is named backpropagation. Backpropagation is a fancy name for a recursive algorithm that computes the derivatives of a nested function using the chain rule while caching intermediary derivatives. I hope that you remember the chain rule from high school. So let's assume that we have a function y, which is defined of two nested functions like f and g. So g takes x as input and returns a value, and the output of g is given to f as another function. This parenthesis is not. We don't need this parenthesis. This parenthesis is extra, so forget it. So we have x as input, and then we take gx as the output, and then we use gx, the output of the gx as the input of f, and the output of f is the value of y, right? So we say that the derivative of y or f with respect to x equals to derivative of f with respect to g and derivative of g with respect to x, which can be multiplied by derivative of g with respect to x, which can be written like this as well, right? So when we do not put anything here, it means it's multiplication, right? So yeah, this is chain rule. And why is this important? Because as we discussed, neural networks are nested functions, so we can use chain rule to get the gradient of neural networks. So backpropagation consists of two steps. A forward pass that we use the current parameter values to compute the loss value, and backward pass that we use the gradient of the loss to update the parameter values. Let's look at an example. I demonstrate these two steps by an example, but I want you to do this example by hand on a piece of paper and try to figure out each step yourself before I explain to you what is the next step. Okay, so we start from x as input. So let me use my pen to do some annotation. So we start with x as input, and then we give x to the first layer of our network. And let's say x, it means we multiply that by a weight matrix for W1, or the weights that we have for the first layer, and then we give them the output of this multiplication to an activation function. So f could be a tangent hyperbolic, or f can be a sigmoid function. Let's call the output h1, or hidden variable 1, right? Then we use the output of the first layer as the input to the second layer. So we use h1 and we multiply that by weights that are defined for the second layer, and we use the same activation function and we get h2. And then we use the third layer and we get y hat, right? And the output of the third layer is y hat, or the output predicted by our network. But what was our goal? Our goal is to predict a true label y. So we want to know how far is this output predicted by our model from the true label given in the training set. So how should we measure the difference between these two? By a loss function. So we give y and y hat to the loss function, and we compute the loss. And this is the end of the forward pass. And then we are done with the forward pass. And now we can do the backward pass. For the backward pass, we need to measure the gradient of this function with respect to all parameters that we have, right? But here we have a nested layer, so we cannot directly compute the gradient of L with respect to all parameters. So what we do in practice is that we calculate the gradient layer by layer and go from top to down in the opposite direction. So that's why it's called backward. So what we can do first is to calculate the derivative of L with respect to y hat, right? So let's say we call it the derivative of L with respect to y hat. We can calculate it because this is a direct a function, which is a function. We don't need any chain rule or anything here. And so it is more or less similar to, it is exactly identical with the gradient of L with respect to f. Right? Let's assume that we save the value of this gradient in a variable named d3. So let me mark it here. Okay. So d3 is a variable, and I want to say that d3 is the error that the model sees at this step, right? So the error that can be associated to the third layer, right? Okay. What else can we do? Okay, now we want to calculate the derivative of L with respect to W3. So let's see if we can find the chain here. The chain is here. We want to calculate L with respect to W3, right? So L depends on F, and F depends on W3. So we need to calculate the derivative of L with respect to F, L with respect to F, which is the first term here. And then we need to calculate the derivative of L, the derivative of F with respect to W3, which is the second term here, right? What is the derivative of L with respect to F, the first term? The derivative of L with respect to F is D3, right? And what is the derivative of F with respect to W3? Derivative of F with respect to W3 is its coefficient, or H2, right? So the value here is D3 times H2, right? So the derivative of this, the derivative of loss with respect to parameter in the third layer is equal to the error at the beginning of the layers times the coefficient that we have, or the input of the layer, or H2. right? That's why we need to save H2 in the forward pass. Okay. Now we can clear these drawings. And okay, so let me find it. Okay, so we clear this and we go to the next layer. But before going to the next layer, let's see if we can estimate. I told you that this is the error in these steps, but can we see what is the error in this step? The error in this step is the error, the input to this, D3 gets in, we multiply that by the weights, W3, and the error in this step is D3 multiplied by W3, right? So because the weight is here, so D3 is input, so this layer multiplies that by W3 and it gets H2, right? So, okay, perfect. So let's go to the next step. So let's assume, okay. Let's assume that we save D3 multiplied by W3 into variable D2. Actually, here we need a parenthesis. Yeah, here we need a parenthesis. Something like this. Okay. Okay. Well, it doesn't impact what we are going to do. So let's say we save this value in D2 and we continue our equation. Now we calculate the derivative of L with respect to W2, which equals to we need to find a chain. L depends on F. F depends on H2, right? F depends on H2, and H2 depends on W2, right? W2. So the first arrow here, or the first piece of chain is this part, which is the derivative of L with respect to F. The second part is derivative of F with respect to H2. And the third part is derivative of H2 with respect to W2. The derivative of L with respect to F is this, if this is D3, right? So derivative of F with respect to H2 is W3, right? And derivative of H2 with respect to W2, H2 with respect to W2 is H1. So we can rewrite this as this. Derivative of L with respect to F is W3. Derivative of H2 with respect to W2 is H1, right? And derivative of L with respect to F is D3, all right? And we said that D3 times W3 is D2, so we can say it is D2 times H1, all right? So the error, yeah, so as we can see here, the derivative of the loss with respect to the parameter of the second layer equals to the error at this point times the input to the layer. So the error at the end of the layer times to the input of the layer. So this is the derivative of this layer. Okay, now we can go to the next saving. So we can say, okay, the derivative of D2, we multiply D2 for the error at this point by the weights of this layer, and this is the error at this step. So D2 times W2 is D1. And yeah, and based on that, we can calculate the loss for the first layer. The loss for the first layer, we need to find the chain first. L depends on F, F depends on H2, H2 depends on H1, our H1, and H1 depends on W1, right? So L depends on F, so run the derivative of L with respect to F derivative of f with respect to h2, derivative of h2 with respect to h1, and derivative of h1 with respect to w1. So what is the derivative of L with respect to F? It is D3. Derivative of F with respect to H2, it is W3. Derivative of H2 with respect to H1 is W2. And derivative of H1 with respect to W1 is X, right? So the derivative of loss with respect to the parameters of the first layer equals to the error at the top of the layer times the input to the layer. So if we say the error at this step is D1, the derivative of loss with respect to the parameter equals to the error at this point times the input here. The derivative of the loss with respect to the parameters in this layer equals to the error at this point times the input here, right? And the derivative for this layer equals to the error at this point times the input that we have here. So in order to implement this forward and backward pass, the only thing that we need to do is to save H1 and H2 and the loss value, right? So, and we only calculate the derivative of loss with respect to y hat, and we save it in D3. And after that, everything works computationally. So we say whenever we need to calculate the derivative of loss with respect to parameters in the third layer, we just multiply D3 with D3 by the value of H2. So, and when we want to find the loss with respect to the parameters in the second layer, we multiply the error and this step that we save it in variable D2 times the input or H1. So, and here we multiply that D1 by X. So by saving two set of variables, so let's say if we save a list of hidden values like H1, H2, and the output in the forward path, and saving D3 and D2 and D1 in another list, then we can implement backpropagation algorithm easily. And the only derivative that we need to calculate is the derivation of loss with respect to y hat. Okay, so as we discussed, the output of the backpropagation algorithm is gradient of parameters of a neural model. So now we have the gradient of all parameters in a neural model. So once we have the gradient, we can use a stochastic gradient descent rule to update the parameter values. It is important to distinguish between these two algorithms. As the backpropagation only computes the forward path and backward path. It only calculates and saves the gradient values. That's it. It doesn't do anything more. The algorithm that updates the parameters is a stochastic gradient descent. Okay, so let's look at a simple training loop in PyTorch. PyTorch is a framework for designing or for defining neural models and also training a neural model. In many algorithms are already implemented in PyTorch, so the only thing that we need to do is to define a training loop. So a simple training loop in PyTorch looks like this. We have an optimizer, for example, a stochastic gradient descent. So let me use my pen again. We have one optimizer, which is a stochastic gradient descent, whose task is to update the parameters. So as the input, it receives some parameters of the model and some learning rate or step size, and it knows how to update the parameters. Now we update, we run our learning algorithm. Here we have a concept of epoch. Epoch is when we say we process the data for one epoch, it means we go through the whole training set at one time. So we process all the samples in the training set. So for epochs in a range of number of epochs, let's say this is the criteria to stop training. So we say we want to train the data, we want to train the model on this training set for 100 times, for 30 times, for 20 times. So we go through this data and we update that. And we want to do it in a mini batch setup. So we assume that we receive the data back in a batch-wise setting. So we receive that in a set of batches or in list of batches. And X is the input and Y is the output. So the model receives X and it returns Y hat. So for any example that we have in the batch, the model returns some output, right? The model returns one output. And then we give this one hat and the true label that we have it here to the loss function, and we receive the loss back, right? For a second, let's skip this line and we move to this one. And then when we have the loss, so here is the end of forward pass, right? Now we did the forward pass, and here we want to do backward pass. We compute the gradient. So by calling loss.backward, we compute the gradient of the loss, and then we save all D3, D2, and D1, right? So we compute the gradient as we discussed, and then we call optimizer.step. Optimizer.step actually updates the parameters. And as you notice here, the step that we update the parameter is done by the optimizer, which is a stochastic gradient descent. But the forward and backward is calculated in the backpropagation algorithm. Okay, but what is this optimizer zero graph? This is a technical solution to in PyTorch to avoid adding gradients in different iterations. If you do not use this command, your gradient will be added at each iteration. So D3 and D2 and D1 will be communicated. And this is not something that you want to do. So this is more or less needed for PyTorch. Okay. Now that we discussed about optimization training as an optimization problem, and we also discussed about backpropagation, now we want to talk about language models. As a fundamental language modeling is known as a fundamental machine learning natural language processing task. And the goal of the task is to assign a probability to a sentence in a language. So we want to know what is a probability of seeing the sentence, the cat sat on the mat in English, right? So the ideal performance at language modeling is to predict the next token in a sequence with a number of guesses that is the identical or lower than the number of guesses required by a human expert. So if you bring, for example, a native speaker and ask the cat sat on the, you ask the human, your human expert to fill the gap or the blank, then your human expert should be able to say 5 words can fit here, and your model also should be able, ideally, either 5 or lower, not more than that. But this is a very ideal scenario, so we don't expect our language model works equally good as humans. So but the point is that even without achieving human level performance, language modeling is a crucial component in real world NLP applications, such as conversational AI, machine translation, and text generation, or any text generation algorithm problem. Okay, let's look at the language models. Let's assume we have the sequence of words, W1 to N, and we want to know how likely this sequence of words is. So the probability of this sequence of words equals to the probability of W1. So because this is the first word, so how likely is to see W1 in this language? And as the first token. And then we have the probability of W2 given W1. So we want to know what is the probability of the second token given the first token, right? And then what is the probability of the third token given whatever that we have seen in the previous tokens. And finally, we want to say what is the probability of the last token given all tokens in all other tokens in the sentence. So more or less, for predicting the probability of these tokens, we look at these sequence of token as context. So this is what we know as context in language, right? Okay. But what is the problem? The problem is that when you want to calculate the probability of these tokens, you need to find all combination of these n-1 tokens. And since the number of words in a language is a lot, where the vocabulary size is very large, very big, and then the number of combination of these words grows exponentially. Right? And therefore, it's very expensive to find an accurate value of these combinations. So what we can do is to look at the Markov assumption in a statistic. The Markov assumption says that the future is independent of the past given the present. So if we know what the status is in the present, then we don't care about the past about the events that happened in the past. We assume that all the knowledge that we need to predict future is summarized in the present event. So this is called first order Markov Markov assumption. And if we assume that the knowledge that we need to predict future is collected in the current status, and all the one before that is called the second order Markov decision, and so on. So we can define case order Markov assumption that assumes that the next word in the sequence depends only on the last k words. So the probability of Wi given Wi minus 1 depends on k words before this and before this. So we don't need then to look at the words from or all the combinations of words from the first token until the current token. We just look at the k last token or last k words. So therefore, the probability of a sequence of tokens can be defined like this. So the probability of a sequence of token is the product of the probability of words of each word given the k words context. However, computing this product is difficult for computers. You can think of why this is a problem, and you can write us. The problem, or you can write us in the comments, for example, that why computing this product is difficult for computers or for machines. What we do usually as the solution is that we compute the log of the probability. So instead of computing the probability directly, we compute the log of the probability. And since we have the log, and log of product is the summation of logs, right? So we can easily write it like this. And instead of product, we have sum, and then we do not have any computational issue. Okay. But how should we evaluate language models? The common metric to evaluate language models is named perplexity. It's defined over an unseen sentence, and it indicates how well a language model predicts the likelihood of the sentence. So if we assume that the perplexity of language model is given here, and for a given sentence W1 to n, The perplexity, so let me use my pen. Okay, the perplexity of this is computed like this. So you compute the probability of each word. So let's say language model is nothing more than a probability over vocabulary. So it's the probability of each word given its context, right? It's the log probability or log likelihood of each word. And then you compute the average of those, right? And if it's very likely, so let's say all words have a probability 1, right? So the log of all of them are 0. So this sum is 0, this average is 0. And when the average is 0, then we have 2 powered by 0. So the perplexity, the value of the perplexity is 1. So for 0, so if we derive it, if we throw it like this, x is the probabilities or the input, and y-axis shows the perplexity. When the probability is 0, the perplexity is 1, right? Is 1. And when perplexity, and let's say when the probabilities are, no, excuse me, when the probabilities is 1, perplexity is 0, so we are here, right? And this is what we discussed. So we said when the probabilities are 1, so if the sum is 1, if this is if the language modeler returns 1, then the log of 1 is 0, right? So then this sum, this average is 0, and 2 powered by 0 is 1. So we are here, right? And when let's say when the probability is 0, so when language modeler returns 0, then the log is plus infinity. Then the log is minus infinity. Yeah, the log is minus infinity, and then the average of this is average of n minus infinity is minus infinity, and minus by minus is plus infinity, right? Plus infinity, and 2 powered by minus infinity, it goes up. So it's like we go something like this, right? So the perplexity function, is a decreasing function, So if you work better, the perplexity is lower. So this is important to notice that um, lower perplexity values indicates a better language model as it assigns higher probabilities to the unseen sentence. The other fact that you should notice is that perplexity of the language models are only comparable with respect to the same evaluation data set. Although in the same language, you need to evaluate on the same unseen sentences, because sentences all could be all in English, but still have different distribution. So it is very important that we fix this W1 to N, and the input is language model. Okay. The only question is, how should we estimate the probability? The first answer, or the traditional answer, is to count. So we can estimate each probability by looking at the frequency of the event in one corpus, right? So let's use this notation to refer to the count of the sequence of words, Wi to j in a corpus. And then we can use maximum likelihood estimate, or MLE, of the probability, which is the number of times a sequence of words happen divided by the number of times that its context happens. So as an example, consider W1, W2, and W3 would be equal to the cat sat. So we have a sequence of the cat sat. So what we do is that the numerator is the frequency of the whole sequence, the cat sat, and the denominator is only the frequency of the context or the cat or this part or the cat or this part. Let me clear my drawings and then we can go forward. Okay. Okay. But it's very likely that the frequency of a sequence of words would be equal to 0. But why does it happen? Because the number of samples that we have in the training set is limited, and usually the samples that we have in the training set do not represent all sentences that we can create in a language. The other reason is that language is always evolving. New words emerge, and new combination of words will be used in different time spans. So it's very likely that the probability of or the frequency of a sequence of words would be 0. But why is it a big deal? It matters because when the probability estimation is 0, when the frequency is 0, then the probability estimation is also 0, which translates to an infinite perplexity. So one way to avoid 0 probability of n-grams is to use smoothing techniques. The easiest smoothing technique is additive smoothing. So the idea is that if we say that this is the frequency of sequence of tokens and it's going to be 0, what we do is that we add the parameter value here. So we add a small tiny number here like alpha between 0 and 1, and then we use this sum as the denominator, right? And for the denominator, we use this. For the denominator, we need to use the vocabulary size as well, because we, for the context, any word in the vocabulary can be the context. Can be the context. Can be used after that context. Okay, let's discuss about the advantages and disadvantages of the traditional language model. They are easy to train and they can easily scale to large corpora. They are easy to train because all you need to do is just to count, right? So you don't need to do any optimization or anything. And it works pretty well in practice. But the point is that it is scaling to larger n-grams is a problem for MLE-based language models. So when you have a longer sequence of context or n-grams, then your vector would be quite sparse because there are different combinations of them, and they rarely happen in the data set. They rarely occur in the data set. So it's very likely that you get 0 count for most of the n-grams. And the other point is that MLE-based language models suffer from lack of generalization across contexts. What does that mean? It means that if during the training we observe black car and blue car, and during the test time you see red car, it gives the red car very, very low probability. Why? Mainly because it has not been observed during training. But as a human, we know that black, blue, and red are related to each other semantically. In other words, traditional language models do not use linguistic information. They only focus on statistics of the language. So to see how often words co-occur with each other in a training set. To overcome these issues, we can use neural language models to estimate the probabilities. In this way, we can overcome the shortcomings. So because neural networks allow to condition on increasingly large context size, so we can use larger n-grams, because as we discussed, the conditioning in neural network, it means that you use the given part or the condition bar part of the probability as the input to your neural model. And they support generalization across different contexts. So, so if you have blue card, black card, you know that blue and black are colored. So red is also color. So they are semantically related. So red color, it should also have high probability. So we focus on the neural language model that was introduced by Benjo and colleagues in 2003. Let W1 to K be the given context, and we want to estimate the probability of the next token given the context. Right? We design a multi-layer perceptron neural model, which takes the, so let me use my pen again, which takes W1 to K as the context. As I said, whatever that we have in the condition part would be the input to our neural model, and the output would be the probability of the token in position K plus 1 over all vocabularies, over all words that we have in the vocabulary. So X would be the vector representation of each word in the context. So vector representation of the first word, vector representation of the second word, until the last word. So X is the matrix representation of the context. We give it to a hidden layer or the feed-forward neural model, and we use G as a nonlinear activation function, and we get H1, and then we use H1 as the output to the next layer. We give it to the W2, we multiply that by the parameters of of this layer, and we also use bias, and then we receive some scores over all vocabularies that we have in the language. But since these scores are not probability, we use the softmax function to map these scores to some probability distribution or to probability space, meaning that the sum of these probabilities or these numbers should be equal to 1, and each value should be between 0 and 1. Then we pick up then we can find the probability of the word that appeared in position K plus 1 as the probability of the sequence, right? As the probability of that word in position K plus 1. Okay. But the nice thing about neural language model is that the training examples can be simply any k-grams from the training set. So you don't need to use complete sentence. You can use 1 gram, 2 gram, 3 gram, or any n-gram, where you use the k minus words in each k-gram as the context, and the last word you use the last word as the target label for the classification. In other words, we do not use any specific output. We use the word that we have in the input text. So that's why this model also called self-supervised learning. So we use the input X that we have as a learning signal to train our model. And then the loss function is a cross entropy loss. Okay. The nice thing about neural language model is that they can be used for generating a text. So let's assume that we are given a context and we are asked to predict the next words from vocabulary. So what we do, we feed the context to our trained NLP-based language models, and our language model returns the probability of each word in vocabulary, and we pick up the word with the maximum probability to generate the next word, right? And we add the predicted words to the context and repeat the above procedure. In this way, we can generate them. So in this lecture, we discuss about machine learning in general, and we show that the supervised machine learning algorithm can be cast as an optimization problem in maths. And the only thing that we need to do is to compute the loss, and we calculate the gradient of the loss. And then we discuss about different loss functions and regularization terms that people use in NLP. And we discussed that how we can use a numerical method named gradient descent, or the stochastic version of that, to update the parameters, And then we said a stochastic gradient descent is nice, but computing the gradient for deep learning models is difficult. So we need to have an algorithm to compute the gradient. That's why we use backpropagation or backprop, which is an algorithm to compute the gradient in 2 steps, forward pass and backward pass. And we noticed that the way that we go through the forward pass, we save the output of each layers in some variables, and in the backward pass, we can easily compute the errors based on the gradient of the loss, and also the error at each layer. And at the end, we discuss about language modeling as a fundamental task in NLP. And we show that how this task is solved traditionally as a count-based probability estimation, and how is this task treated recently by neural models. That's all for today's lecture. Thank you.